In order to study optimization of multivariable functions a little further, we're going to need a special theorem. Now, to motivate this theorem, we're going to go back to an idea from single variable calculus, and we'll talk about implicit differentiation. Now, as an example, let's take the unit circle x squared plus y squared equals 1. What is the derivative y prime of x here? Now, in order to apply the method you use in Calc 1, you make an assumption that y can be written as a function of x. X would be the independent variable and y would be a dependent variable or a function. And then you make a further assumption that y prime exists. Once you make those assumptions, then you go ahead and you differentiate both sides of the equation. You would apply linearity in the chain rule and you'd get 2x plus 2y times y prime equals 0. So what this did was it allowed you to solve this algebraic equation for y prime, and you would find you'd get a negative x over y. So the answer wasn't written as an explicit function of x, because ultimately we didn't know what y was as an explicit function, but regardless, we were able to find an expression. When can this technique be applied? And now that we've studied multivariable calculus, we'll have enough in the way of machinery to at least state a special theorem called the implicit function theorem. And I'm going to just give it the acronym IFT. And this is just going to be a special version of the implicit function theorem. Capital F of x and y is a function that goes from R2 into R, defined on some set that lives in R2. It contains the point x0, y0. If the function is 0 at that point x0, y0, and its partial derivative with respect to y at that point is not 0, then there is a rectangle that contains x0, y0. And I'm going to draw a picture of it, something like this, such that y equals y of x in this rectangle, and it's essentially near the point that we want. We can't really say anything about its values unless we had some more information about the function. And in terms of a picture, we've got y passing the vertical line test, y equals y of x, so it can be written as a function. The function satisfies y naught is the value that you would get when you plug in x naught into that function, and it also satisfies the original equation, and this would happen all within this rectangle. Now, moreover, this function y has a continuous derivative, and it's going to be exactly equal to the result that we get from the Calc 1 implicit differentiation idea, but written in terms of partial derivatives, it's going to be the following: fx over fy, or the partial with respect to x over the partial with respect to y. And this is true at all points in the rectangle, including the point x0, y0. This idea that we took from Calc 1 actually turns out to work for some fairly easy constraints. Now, this implicit function theorem is saying, in terms of this picture, you can't make your rectangle too big, because it's possible that once you go too far away from this point, your function might start to double back and you'd fail the vertical line test. So there has to be a relatively small box around that point for this to work. Now, the other thing that you should note is if we wanted to just write x as a function of y, so switch the variables around, this is also possible, but what it's going to require is that the x partial derivative at that point is not 0, so that we could just use this in reverse, and we would find that this is what our result would be. It would be negative fy over fx. But we're just going to state it in terms of this version so that we can have our usual y as a function of x. Now, going back to our example here, x squared plus y squared is equal to 1. We could think of this as some function g of x. So this could be interpreted as g of x is equal to 1. But at the same time, we could also reorganize this And then this would be our function capital F of x and y equals 0. So it's always possible to take a function of two variables that equals a non-zero number and always write it as a slightly different function of two variables that does equal 0. So for this function, f of x and y is x squared plus y squared minus 1. The x partial derivative is 2x. The y partial derivative is 2y. The value of that constant doesn't really cause any problems. Now the point 1 over root 2, 1 over root 2. If I were to put that into the function, I would find that yes, it does satisfy the requirement that the function equals 0. So if we take a look at a picture of the unit circle, if we go to this point 1 over root 2, 1 over root 2, the y partial derivative at the point 1 over root 2 is non-zero. The value of the function is 0. So that means that the IFT applies. And what it's saying is that there's some box around that point where y is a function of x. You could see for yourself right here that it's going to pass the vertical line test. Take this formula and reorganize it. Take the square root of both sides. The absolute value of y is equal to this. And as long as we are near that point, y equals 1 over root 2, and as long as we are near x equals 1 over root 2, then this will be completely valid. And yes, we have y is a function of x here. If we wanted y prime, we would take negative x partial derivative over negative y partial derivative. That would give us a negative x over a y. But in this particular case, we know exactly what that y is. Now look, if we were to take this box bigger than the one I drew here, then I would no longer be a function anymore. But the important point is that it gives us some justification behind the ideas that we used in Calc 1, and we're going to need those in the next video.